On a graph of force in newtons versus position in meters, we can easily calculate slope and area. For a specific graph where we're given graph altitudes of 4 and 6 representing 4 newtons and 6 newtons, and a width representing 0.2 meters, our calculation of the slope proceeds by calculating rise and run first, and our interpretation, it relies on our interpretation of the rise and the run, and then the resulting interpretation of the slope. The rise here is 2 newtons, which is the amount by which the force changes between here and here. The run is 0.2 meters, which is the change in position, or perhaps the distance over which that change occurs. So we have a change in force represented by the rise, a change in position represented by the run. Therefore, the slope represents the change in force divided by the change in position. Change in force divided by change in position. And that would be the average rate of change of force with respect to position. The average rate of change is 10 newtons per meter. A change of 2 newtons over a change of 0.2 meters gives you a change of 10 newtons per meter. Okay? To get a meter, you have to have 5 of these. And then if you had 5 of these, you'd have 10. So that's 10 newtons per meter. Now, that 10 newtons per meter is only an average that only applies over this 0.2 meter interval. So we wouldn't extend that out for a whole meter unless we knew that the position, or the force versus position, was in fact a linear graph. Okay, so we reason out the fact that a 0.1 meter change in position then implies a change in force of 10 newtons per meter multiplied by 0.1 meters or 0.1 newtons. In that calculation, and of course the units work out here in the way that we're hopefully accustomed to, that calculation is consistent with just what we would get using ratios. 0.01 meters is 1/20th of 0.2 meters, so we have 1/20th of this 0.2 meter width. That should give us 1/20th of the 2 newton change in the force. Well, 1/20th of the 2 newtons is 0.1 newtons. So that's all very consistent. Okay, so this interpretation is relatively straightforward, but of course it takes a little bit of getting used to. Now we interpret the area. Well, area is average altitude multiplied by width, which represents average force times change in position. The average force here between 4 and 6 newtons is obviously 5 newtons, assuming the linear approximation to be correct. Yeah, maybe a good assumption, maybe not. 0.2 meter change in position, or, well, yeah, 0.2 meter change in position, then we get 1 newton times meter. Now I've written the fact that that's 1 joule, but let's ignore that for a minute and let's think of the question that led to this. Okay? First of all, force exerted through a change in position does work and requires energy. If I push a car 10 meters with 1 force, then push it 10 meters with a greater force, we expect it to attain a greater speed, therefore a greater kinetic energy. So my greater force did more work. I'm going to feel it that way. And requires energy and results in a change in energy within a system. Now that's all pretty vague and needs to be made very specific, but that's the general idea. Excuse me. Now, so we say that this 1 newton meter is the amount of work done or the energy expended by the 5 newton force acting through displacement 0.2 meters. Now, if you're seeing these videos in sequence, you know that we have already said that in general this quantity is going to have a meaningful interpretation provided this quantity is a rate of change of some other quantity. That is, our force in this case would be the rate of change of some other quantity with respect to the quantity measured in this direction. So force should be the rate of change of some quantity with respect to position. How do we reconcile that? Well, Again, 1 Newton meter is the work done or the energy expended by 5 Newton force through displacement 0.2 meters. Let's give that Newton meter a name, the joule. Okay, so now if the joule is our unit of energy, then through even general science you should have seen this at some point, whether you remember it or not. The joule is a unit of energy, and it's equal to a Newton times a meter, so that a Newton is a joule divided by a meter, so Newton is a joule per meter. Well, then joule is a measure of work or energy, so this is work or energy per meter, so that force is now an average rate of change of energy with respect to position. And now we can say that 5 newtons is the average rate at which energy is expended with respect to the changing position. And 5 newtons, being 5 joules per meter, can be multiplied. That's our average force can be represented as 5 joules per meter, and multiplied then by our 0.2 meter displacement, giving us 5 joules per meter times 0.2 meters, which gives us the 1 joule, which is of course the same as 1 Newton meter. So we've used the general principle about the meaning of graphs and the fact that this should be a rate of change of something with respect to this, and figured out what that something should be, and it turns out that it has a fairly sensible and tangible interpretation as work energy.